In this video, we're going to talk about how to find a Taylor series and a Maclaurin series for different functions. So let's start with this example. Let's find the Taylor series given the function f of x is equal to ln x centered at c equal 1. So what we need to do is basically write out the first four derivatives. So f prime of x, the derivative of ln x, that's 1 over x. Now to find the second derivative, we need to rewrite it and then use the power rule. So the second derivative is negative 1 divided by x squared. And then to find the third derivative, let's use the power rule again. So for the third derivative, it's going to be 2 divided by x cubed. And then to find the fourth derivative, it's going to be negative 1 times negative 2, that's positive 2. And then we need to take the derivative of x to the negative third power. So that's negative 3x to the negative 4. So the fourth derivative is negative 6 divided by x to the fourth power. Now the next thing that we need to do is evaluate the function and the derivatives at c. So f of 1, c is 1, that's going to be ln 1. The natural log of 1 is 0. And then f prime of 1 is going to be 1 over 1, which is 1. And then the second derivative, evaluated at 1, that's negative 1 divided by 1 squared, which is just negative 1. And for the third derivative, it's going to be positive 2. And the value for the fourth derivative, when x is 1, is negative 6 divided by 1 to the fourth, or simply negative 6. So now we can get rid of this stuff. Now this is the formula that you want to use to write the expanded form of the Taylor series. So it's f of c plus f prime of c times x minus c to the first power plus f double prime of c times x minus c to the second power divided by 2 factorial plus the third derivative evaluated at c times x minus c to the third power divided by 3 factorial, and then it just continues. So f of x, which is ln x, we could say that it's equal to f of c, which is f of 1, and we know that f of 1 is 0, and then plus f prime of c, which is 1, times x minus c, c is 1, and then the second derivative, that's going to be negative 1, so that's f double prime of c times x minus c to the second power divided by 2 factorial, and then for the third derivative, that's going to equal 2, so that's going to be plus 2 times x minus c to the third power divided by 3 factorial, and then we have negative 6 x minus c to the fourth power divided by 4 factorial, and then that's going to continue. Now let's simplify what we have. So we don't need to write 0. So we could say that the natural log of x is x minus c to the first power divided by 1 factorial, and then minus, well, I need to get rid of the c. This is supposed to be x minus 1 to the first power. And then it's going to be minus x minus 1 squared divided by 2 factorial, which is simply 2. And then plus, what is 2 divided by 3 factorial? 3 factorial is 3 times 2 times 1. And so we can cancel the 2. So therefore, this is going to be plus x minus 1 to the third power divided by 3. I'm just going to write this as 1 so you can see the pattern. And then we're going to have, this is going to be negative. Now, 6 divided by 4 factorial. Let's simplify that. 4 factorial is 4 times 3 times 2 times 1. So 6 will cancel with 3 times 2. So this is going to be x minus 1 to the 4th power divided by 4. So now we could see a pattern developing. So how can we write this series using summation notation? So let's start with n equals 0, and we're going to go to infinity. So when n is 0, we need to get 1 as an exponent. When n is 1, we need to get 2. And when n is 2, we need to get 3. So therefore, it's always 1 more than our n value. So we're going to have n plus 1. So this is going to be x minus 1 raised to the n plus 1 power. And since these numbers are the same, we need to have an n plus 1 expression on the bottom. Now the last thing we need to deal with are the alternating signs. It's going to alternate from positive to negative to positive and so forth. So we can either use negative 1 to the n or negative 1 to the n plus 1. Which one should we use? Now when n is 0 for the first term, we need to get a positive sign. Negative 1 to the 0 power is positive 1. So we need to use this one. And so I'm going to write that here, negative 1 to the n. So this is the Taylor series for the function ln x centered at c equal 1. And you can see the x minus 1 term, which tells us that it's centered at c equals 1. For the sake of practice, let's go ahead and try another example. So find a Taylor series for the function f of x equals e to the x centered at c equals 3. So go ahead, pause the video, and take a minute to try this problem. Just like before, let's make a list of the function and its derivatives. So we have the function e to the x. The first derivative is going to be e to the x, as well as the second, the third, and the fourth. So all of the derivatives will be e to the x. Now, f of c, which is basically f of 3, that's e to the 3. And that's going to be the same as f prime of 3, f double prime of 3, and all of the derivatives, they will all be equal to e to the third power. Now let's write out the function. So f of x is going to equal f of c plus f prime of c times x minus c to the first power plus the second derivative times x minus c to the second power divided by 2 factorial, and then it's going to be the third derivative times x minus c to the third power over 3 factorial, and then that's just going to continue. So our f of x is e to the x, and f of c, or f of 3, that's e to the third power. F prime of c is going to be the same thing, e to the third power, but times x minus c, where c is 3. And then f double prime of c is also going to be e to the third power, and then it's going to be times x minus 3 to the second power over 2 factorial, and then it's going to be e to the 3 x minus 3 to the third power over 3 factorial. Now we need to write a general power series that will give us what we see here. So starting from 0 going to infinity, we can see that the e to the third part, it doesn't change. So that's pretty much constant. Now the only part that changes are the exponents and the factorials. Therefore, we need to represent those numbers with something that contains the letter n. The only other part that doesn't change is x minus 3 for every term. Now when n equals 0, we have the e to the third term. When n equals 1, we're going to get this term. And then this is for when n equals 2 and when n equals 3. And so notice that the n values matches with the exponents and the factorials. So therefore we can say that this is x minus 3 to the n power divided by n factorial. And this is the Taylor series for the function e to the x centered at c equals 3. Let's move on to our next example problem. Number 3. Find the Maclaurin series for the function f of x is equal to sine x. The only difference between a Taylor series and a Maclaurin series is that c equals 0 for the Maclaurin series. So that's why there wasn't any c value given to you. Now the first derivative, which is the derivative of sine, that's going to be cosine. And then the second derivative is negative sine x. And then the derivative of negative sine, that's going to be negative cosine x. And then the fourth derivative is going to be the original sine x function. Now the fifth derivative is the same as the first, and the sixth derivative is the same as the second, and the pattern will repeat. So to evaluate f of 0, that's going to be sine 0, which is 0, and then f prime of 0, cosine 0 is 1, and then f double prime of 0, that's negative sine 0, so that's 0. And then for the third derivative, it's going to be negative cosine of 0, which is negative 1. And for the fourth derivative, sine of 0 is 0. And so this is going to be the same as the fifth derivative, and this is the sixth, the seventh, and then the eighth. Now let's write out the function that we need in order to get the Maclaurin series. So f of x is going to equal f of c, but instead of f of c, we're going to replace c with 0. So it's going to be f of 0, and then plus f prime of 0 times x minus c to the first power, so that's x minus 0 to the first power, which we can simply write x to the first power. And then it's going to be the second derivative at 0 times x squared over 2 factorial plus the third derivative at 0 times x cubed divided by 3 factorial. And then that's going to continue. So f of 0, we could see that it's equal to 0. And then f prime of 0, that's equal to 1. So we're going to have 1x, and then plus f double prime of 0, which is 0. And then the third derivative, it's equal to negative 1. So it's going to be negative x cubed over 3 factorial. And then the next term for the fourth derivative is going to be 0. And then plus the fifth derivative. So it's going to be 1 times x to the fifth over 5 factorial. And then plus 0. And then minus, for the seventh derivative, negative 1 times x to the 7 divided by 7 factorial. Now let's simplify what we have so we can get rid of all of the zeros. So our function, which we can write as sine x, that's equal to x, which I'm going to write as x to the first power divided by 1 factorial, and then minus x to the third power divided by 3 factorial, plus x to the fifth power over 5 factorial, minus x to the 7th power divided by 7 factorial. And the series will go on forever. So now let's write a general expression for that series. So let's start from 0 to infinity. So when n equals 0, we need to get x to the first power over 1 factorial. And when n is 1, we need to get 3. So let's write down the sequence. So the sequence of numbers are 1, 3, 5, 7, 9, 11, and so forth. So when n is 0, we get 1. When n is 1, we need to get 3. When n is 2, we need to get 5. And the pattern will continue. Now what we have is an arithmetic sequence. And to write the general formula for an arithmetic sequence, we can use this equation. So our a sub 1 term, that's when n is 1, that's going to be 3. And the common difference, we could see that is 2. All of the numbers are increasing by 2. And so we have the expression a sub n is 3 plus 2n minus 2. 3 plus negative 2, that's 1, so we're going to get 2n plus 1. And so this is going to be x raised to the 2n plus 1 divided by 2n plus 1 factorial. Since these numbers are the same, so therefore they share the same general formula. We just have a factorial symbol at the bottom. Now the last thing we need to deal with are the alternating signs. So the first sign is positive when n is equal to 0. So therefore we need to use negative 1 to the n power, because negative 1 to the 0 power will give us positive 1. So this is the Maclaurin series for sine x. Now in this problem, we're going to find the Maclaurin series for cosine x using the Maclaurin series for sine x. So in the last problem, we saw that the Maclaurin series for sine x was x minus x to the third power divided by 3 factorial plus x to the fifth power divided by 5 factorial minus x to the 7th power divided by 7 factorial. And this is going to continue all the way to infinity. So what we're going to do is take the derivative of both sides. So on the left side, we have the derivative of sine, which will give us cosine x. On the right side, the derivative of x is 1. The derivative of x cubed is 3x squared. And 3 factorial, we can write it as 3 times 2 times 1. And 2 times 1 is 2 factorial. So the next number is always 1 less than the previous number when dealing with factorials. Okay, I'm not sure what just happened here. Now, the derivative of x to the 5th power is 5x to the 4th power. And 5 factorial, I'm going to write that as 5 times 4 factorial. Now, the derivative of x to the 7th power is going to be 7 times x to the 6th power. And let's write 7 factorial as 7 times 6 factorial. Now, let's cancel the 3. We could cancel the 5. And let's cancel the 7. So we're left with cosine x is 1 minus x squared divided by 2 factorial plus x to the 4th over 4 factorial minus x to the 6th divided by 6 factorial. Now, how can we represent this series using summation notation? Now, the first thing I need to do is make some space, because I'm always short of it using this board. So what patterns do you see? Now, keep in mind, when n is 0, we need to get 1. When n is 1, we need to get the exponents 2 and a factorial 2. And when n is 3, we need to get 4 factorial. I mean, not 3. I skipped 2. When n is 2, we need to get 4 factorial and x to the 4th. And then when n is 3, we need to get 6. So notice that the exponents and the factorials are always 2 times the n values. So therefore, this is going to be x raised to the 2n. divided by 2n factorial. The last thing that we need to talk about are the alternating signs. So the first sign is positive. So just like before, we're going to use -1 to the n power. So this is the Maclaurin series for cosine x. Now, there's another simpler way of getting the same answer. I'm going to show it to you. So we're going to start with this expression, sine x, which we said was the series from 0 to infinity, and it was x to the 2n plus 1 times -1 to the n divided by 2n plus 1 factorial. So all we need to do in this example is we just got to take the derivative of both sides. So the left side is going to become cosine x. Now what about the derivative for the right side? So let's rewrite the summation notation. And we need to realize that -1 to the n is a constant. 2n plus 1 factorial, that's a constant. So the only thing we need to take the derivative of is x to the 2n plus 1. And let's use the power rule. So based on the power rule, the derivative of x to the n is nx to the n minus 1. So we need to take the exponent and move it to the front. So that's going to be 2n plus 1 times x, and then we need to subtract the exponent by 1. So let's do that. What is 2n plus 1 minus 1? So we know that's going to be 2n, and then divided by. Now this constant, we're just going to rewrite it. So that's going to be -1 to the n power. Now this constant will remain, but we want to cancel the 2n plus 1. So we're going to adjust the 2n plus 1 factorial. Now recall that a factorial is 8 times 7 factorial. And so we're going to do something like this. So first, we're going to write the first number. In this case, that's 2n plus 1. And then the next number is going to be 2n plus 1 less 1. To get the 7 is just 8 minus 1. So to get the next number, it's going to be 2n plus 1 minus 1, which is 2n factorial. Now we can cancel 2n plus 1. And this gives us this answer, as you can see. So that's the second way to get the Maclaurin series for cosine x. Number 5. Find the Maclaurin series for cosine x squared. So based on the last problem, we saw that the Maclaurin series for cosine x was this expression. So it's -1 to the n times x raised to the 2n divided by 2n factorial. So if that's cosine x, what can we say about cosine squared? All we need to do is replace x with x squared. So this is going to be -1 to the n times x squared raised to the 2n divided by 2n factorial. Now when you raise one exponent to another, you need to multiply. So 2 times 2n is 4n. So therefore, we can write the series for this composite function as -1 to the n times x raised to the 4n divided by 2n factorial. And this is the answer. So that's the Maclaurin series for cosine x squared. That's what you need to do if you have a composite function. Now let's try this one, number 6. Find the Maclaurin series for x cosine x. So how can we do this? If you recall, the Maclaurin series for cosine x is this expression. It's going to be the power series of -1 to the n times x raised to the 2n divided by 2n factorial. So all we need to do is multiply x by x to the 2n. And so this is x to the first power. Therefore, we need to add 1 and 2n. So the Maclaurin series for x cosine x is going to be the summation from 0 to infinity of negative 1 to the n times x raised to the 2n plus 1 over 2n factorial. And that's all you got to do for this problem. Now let's find the Maclaurin series for the function x squared e raised to the negative x. And this time, use the data table with the list of elementary functions provided by your calculus textbook. Now, e to the x is equal to the series from 0 to infinity x to the n over n factorial. So if that's e to the x, what is e to the negative x? So therefore, e to the negative x should be equal to the series of negative x to the n over n factorial. So all we need to do is replace x with negative x. Now what can we say about negative x to the n? Negative x can be written as negative 1 times x. And this is all affected by the exponent n. So let's distribute n. So this becomes negative 1 to the n times x to the n. So we're going to have x squared times the series of negative 1 to the n, x to the n, divided by n factorial. Now at this point, we can multiply x squared by x to the n. So all we need to do is add the exponents. So 2 plus n, we can write that as n plus 2. And so this is going to be the final answer. So we have the series from 0 to infinity, negative 1 to the n times x raised to the n plus 2 over n factorial. So that's equal to x squared e to negative x. And this is the final answer. Let's work on one more problem. Find the Maclaurin series for the function f of x equals cosine squared. So what can we do with cosine squared of x? We can use the power reducing formula for cosine squared, which is 1/2 times 1 plus cosine 2x. This comes from the double angle formula of cosine 2x, but you rearrange it to solve for cosine squared. Now we know that cosine x is equal to this expression. It's negative 1 to the n times x raised to the 2n over 2n factorial. So therefore, cosine 2x is going to be this expression. It's going to be negative 1 to the n times 2x raised to the 2n divided by 2n factorial. So all you need to do is replace x with 2x. And that's it for this problem. So you can leave your answer like this if you want to. And so this is the Maclaurin series for cosine squared x.